Section 2.1 is on relations and functions. A relation is a set of pairs of input and output values. It can be expressed as a set of ordered pairs, a mapping, a table of values, or a graph. And here's a representation of that from your textbook. Here we have the set of ordered pairs where X is our input and Y is our output. Also, we can have a mapping, which is basically two kind of blobs, so to speak, with the input values in one, the output values in the other, and then arrows drawn from the input to the output. A table of values you're probably very familiar with, and a graph. So this is 4 different ways to represent a relation. So here's an example. In the year 2000, the 4 most populous states in millions were California with 32 million, Texas with 21 million, New York 19 million, and Florida 16 million. And the number of U.S. representatives for California were 35, Texas had 32, New York had 29, and Florida had 25. We need to represent a relation for this data using a set of ordered pairs, a mapping, a table of values, and a graph. So the easiest is probably a set of ordered pairs. And so we want curly brackets, and then we're going to put those corresponding values together in parentheses. Now my input is actually going to be the population for each of those states, and the output is going to be the number of representatives. Because if you think about it, from what you know about civics, the number of representatives that your state has is based on its population. So for California, we'll have 32, comma 53. Oops, close parentheses. And Texas is 21, comma 32. New York 19, comma 29. And Florida 16, comma 25. And then don't forget curly brackets because this is a set of ordered pairs. To do this as a mapping, I'm going to label one of these population. I'm going to abbreviate here, and I'll draw kind of a big circular thing here. And the other I will label representatives, which I will abbreviate also, and draw a big circle there. Put the input values in here, or in other words, what I've put is my x coordinate. My output values over here, or my y coordinates. And then draw an arrow from the corresponding input to the corresponding output. Like that. And there's your mapping. To make a table, I'm going to do population in millions. I'll abbreviate that as well. And then here we will have the number of representatives. And then I will just list the input values with the corresponding output values. Okay, and now to make this as a graph, I'm going to need to label my axes here a little bit. So across the bottom here, this is going to be my population in millions. Let me move that down a little bit. Sorry about that, because I need to label my numbers there. Okay, and I'm going to go with, my values go from 16 to 32, so I'm going to go 10, 20, 30, 40, 50. That should be plenty. Across the bottom, and then over here I need number of representatives. And I'm going to also do this. Those numbers go from 25 up to 53. I think I can do something similar here. So 10, 20, 30, 40, and 50. And then just plot a point for each one of those. So 32, 53 would be something right about here. Doesn't have to be super precise. 21, 32. About there. 19, 29, something like that, and 16, 25, right about there. Okay? The domain of a relation is the set of all the inputs, or the x-coordinates of the ordered pairs. The range is the set of all of the outputs, or the y-coordinates. The way I remember this is D for domain comes before R, the range, x comes before y. So in the example above, we need to identify the domain and the range of the relation. And this is going to be in set notation again. No parentheses this time, just the x values that we had. And then for the range, the y values that we had. Okay. Now, a function is a particular type of relation. It's one in which each element of the domain corresponds with exactly one element of the range. Another way to think of this is that there are no repeated x values. Let's take a look at this example. So is each of these relations a function? Here we have a set of ordered pairs 0, 0, 2, 4, negative 2, 4, 3, 9, and negative 3, 9. Yes, this is a function because you'll notice that there's only 1, 0, 1, 2, 1, negative 2, 1, 3, 1, negative 3 as my x values. So yes, there is only one element of the range for each of the elements of the domain. Number 2, here we have a mapping. And negative 1 is mapped to 4, 0 is mapped to negative 2, 6 is mapped to 2, 10 is mapped to negative 2, and 10 is also mapped to 4. So this is not a function because the value of the domain 10 is actually paired up or mapped to two different values in the range. So this is not a function. If we were to write this as a set of ordered pairs, you'd have 10 comma negative 2 and 10, 4. And that would be a repeated x value. If the relation is represented in a graph, you can use the vertical line test to determine whether or not it is a function. If a vertical line intersects the graph of the relation in more than one point at a time, it is not a function. So let's take a look at these two graphs. Use the vertical line test to determine whether the graph of each relation is a function. So I can't show this on the video, but if you were to take your pencil and hold it vertically, straight up and down, and move it across the graph, are there ever two dots on your pencil at one time for A? No, there are not. So this would indeed be a function. It passes the vertical line test. Now for B, if I were to move my pencil across this graph, let's say my pencil were something like right about here, okay, I can see that it crosses the graph right here and here, which actually represents one value of x for two different values of y. So no, this is not a function if we say it fails the vertical line test. A function rule is an equation that represents the output value in terms of the input value. The function rule can be written in function notation as follows. And this is probably what you're more familiar with, y equals 3x plus 2. The input is x, so you choose your values of x that you put in, and the output is y. And you probably remember this from Algebra 1 as well. We have f of x, or function notation. We read this f of x is equal to 3x plus 2. And I really like this because this shows that the input is x because it's actually put into the function, which is represented by f. And here's how you would do it. Let's say if x equals 1, we would say f of 1 is equal to 3 times 1 plus 2, or in this case, f of 1 is equal to 5. The independent variable is the x, and that's the input of the function. The dependent variable y is the output of the function. And we call it the dependent variable because the value of y depends on the value of x that you put into the function. So let's take a look at an example here. So for f of x equals negative 3x plus 2, what is the output for each of the following inputs? So if we have f of negative 4, that means that I'm going to take negative 4 as my x and plug it into f for x. So that's going to be 3 times negative 4 plus 2. So instead of negative 3x plus 2, it's negative 3 times negative 4 plus 2. That's going to give me 12 plus 2, or we would say f of 4 is equal to 14. When my x is negative 4, my y is 14. Let's do this for 0. So f of 0 is going to be negative 3 times 0 plus 2, or 0 plus 2, or f of 0 is equal to 2. And f of my last value here, 0.2, oops, is going to be negative 3 times 0.2. Sorry, that's a little sloppy. Let me do that again. 0.2 plus 2, or negative 0.6 plus 2, or f of 0.2 is equal to 1.4. A function can also model a real-world situation. It's important to identify the independent and the dependent variable in a given situation. The relationship can be described by a phrase such as, distance is a function of time. This means that the distance traveled depends on how much time has passed. How far you go depends on how long you spend getting there. Let's take a look at an example here. A pizza costs $14. The flat delivery fee is $1.50. We need to write a function rule to model the total cost of the number of pizzas delivered. So I need to define some variables. I'm going to let P equal the number of pizzas, and I'm going to let C equal the total cost. So I can say that the total cost is a function of the number of pizzas that I buy. So C of P, the function is the cost, and it's dependent on how many pizzas I buy, is equal to $14 for each pizza plus $1.50 flat delivery fee. The delivery fee doesn't change. I mean, I can order 100 pizzas and it's still $1.50. Of course, I better give them a pretty good tip at that point, but each pizza costs $14. Now we need to evaluate this function for 5 pizzas. So C of 5 is equal to 14 times 5 plus 1.5, and that's going to give me 70 plus 1.5, or the total cost of 5 pizzas is $71.50. So in this lesson, we took a look at relations, different ways to represent them, what makes a relation a function, how to write stuff, how to determine whether something's a function, and how to use a function rule and write something in function notation.